Yeah, we're gonna wrap up chapter 13. Luckily for you guys, chapter 14 is kind of like, I don't want to call it the blow-off chapter in the class, but it's the chapter where you already know everything in it. So there's only one section that's legitimately new content, which is curvature. But everything else is just reminding you, hey, you can take derivatives and you can take integrals. And believe it or not, with a vector component, you can just do it 3 times. And so there's nothing crazy for the rest of the week. But this is a very memory dense section. So that's kind of why it's obnoxious. I will tell you that you're going to use this stuff in here. The context in which you're going to use this content is going to be a lot of chapter 15 and a lot of chapter 16. Because it's the same way where you know the equation of a circle, like for example, or you know the area formula for a triangle. Those things you can just rip out in your memory and use it. And then you can do that to accomplish intermediate steps for problems. What's going to happen is we're doing calculus now in 3 dimensions, which means everything is going to get blown up to 3 dimensions. When you get to integrations and various applications like such, modeling certain scenarios and visualizing stuff, well, that little 2-dimensional circle equation is not going to work for you anymore. We're going to start to need the fundamental descriptions of 3-dimensional kind of quadric surfaces to perform examples on so that you have something to practice with. So that's why this is important. And that's why you just got to memorize it. Now I'll show you ways that make the concept a little easier so it's less brute force memory. But at the end of the day, you just got to sit down and do it. It's only 6 shapes, so it's not too bad.
What about further? What was fun for me? I like derivatives. So
derivatives? The applications of the derivatives. So this one affects the derivative rules, but the application of the derivatives and gradients of such, yeah. Okay, definition. So given a curve, we'll call that curve C, in a plane, we'll call this plane P, and a line, call that one L. And this line we're going to specifically want not in P. In other words, we don't want it to be contained in this plane. A cylinder. Cylinder is the surface consisting of all lines parallel to the line L that pass through C. Pass through, and if you recall, C is the that original curve that we started with. So this can be pretty difficult to visualize just from the words. If you can do it just from the words, that's great, but I'll draw you a picture so we know what's going on. Now, the first thing to help, don't think of cylinder like a soup can anymore. Okay, we're on calculus. So cylinder is going to have a more general meaning here. It's not going to be necessarily restricted to just the typical, soup can cylinder shape. So if you get that out of your mind, then it's a little bit easier to accept this definition as a whole. So here is X, here's Y, here's Z. And so the idea is we're going to have some sort of a curve in 3-dimensional space. So let's just suppose we've got, a curve like this. And so this is our curve C. And then this curve is existing in some sort of a plane. So obviously I can't draw the plane without it being very confusing with the way it's a 2-dimensional whiteboard in 3 dimensions. But the idea is this is locked into a plane. So if you imagine this curve, regardless of how it's moving, it's locked into a plane. And then that's going to tell us that when this line is going to go through, we just don't want the line to be stuck in the same plane. We're going to be in a different plane. So the line L is going to be in a different plane. So it can go like that. This could be L. Now, what does it mean? So the cylinder part, so a cylinder is surface. So we're expecting a surface, and it's going to consist all the lines parallel to L that are passing through C. So here's L, and it's gonna be a whole collection of lines that are parallel to L. And parallel just simply means they're gonna be moving in the same direction. And they're going to pass through C. So here is a line that's parallel to L that's passing through C. And here's another one passing through C, and another one, and another one. And you can imagine that if you were to kind of flesh this out, you have a surface. We're generating kind of like a surface. Think about like a fabric that you can kind of like, manipulate around. And so it's this three-dimensional surface that's kind of curving down and then coming down. So I know that's pretty difficult to visualize on a whiteboard. The textbook has a really nice colored illustration for this. So that's more, definitely read the textbook for this section. But in general, are we feeling good about this definition? Pretty straightforward. So everyone, like you can rip, if you have a piece of paper or something, like take it out. So this could be a cylinder in the sense that if I drew a line straight down the middle of the paper, and I were to kind of hold it like this, say, in three-dimensional space, then that's forming some sort of curve that exists in 3 dimensions. And then, especially with lined paper, you see all those blue lines on your lined paper? That could be like your line L. And so you got all these lines that are parallel and passing through this curve that you've got going on. And so then what the physical sheet of paper is really representing here is the cylinder, because it's that collection of all those points that are falling on all of those parallel lines that are crossing through whatever curve you drew down your paper. So the typical cylinder people are used to is when you happen to orient your curve like a circle like this, right? So if you have some sort of circle that you've drawn on your paper and then you've wrapped it up like this, it's going to look like that soup can kind of cylinder, because now all these parallel lines are wrapping around in a set that's forming a cylinder when you flesh it out. But that's not the only kind of cylinder there can be. So expand the idea of cylinder to pretty much any single shape you can derive from taking some sort of a curve that's fixed in a plane, sticking it in 3 dimensions, taking the line and then fleshing out all the things. So it's kind of like there's all sorts of things you can imagine, like scrolls or towels or things like that, to kind of visualize what's going on with these cylinders. Key facet of this is that it's kind of got that straight edge thing. So what is different is you wouldn't have something like an anthill. I can draw that. So this is very, very different idea than like if you were to take a towel or something and stick a bowling ball in the middle of it, right? And then kind of get the, something that's going to look like that, but then in 3 dimensions. Because now it's not going to be obeying this necessarily, because this is a more rounded around shape. And so those lines would not be parallel. So that's not a cylinder. So, or like if you look at a bowl, that's not a cylinder, because you can't find a single line that all the rest of the things are actually just parallel to. So cylinders do imply this idea of like a sheet, kind of like, it's got some level of rigidity to it, and that level of structure is coming from the fact that you do need lines to be parallel to each other, and those lines aren't necessarily going to be forming into rounded off things or peaks and mounds.
So when you're saying moldable, you meant something more like this, like you'd have the lines would be more rounded out instead of being straight around the curve, through the curve.
Yeah, you ever try to get comfortable when you're falling asleep, put your blanket over, and then it's like you got your foot stuck under, so you use your knee to push the blanket up. That causes like you make a little tent, that kind of thing. That can't happen. You can't create a parallel line to a curve on that, because now you have to accommodate an infinite number of directions, completely different scenario. So that's what the quadric surfaces are going to help us discover. But this cylinders, that's different. That's just going to be you have a line through a curve and then that's it. So you can think of like blinds or drapes, things like that. Then there's something called a trace. And the traces are going to be really helpful for visualizing 3-dimensional space. So I will tell you that you won't necessarily use trace as a major Calc 3 concept, but trace is going to be the language from which you can provide visualizations for yourself in questions that involve 3-dimensional graphs. So here's another definition. Okay. a trace of a surface is the set of points. Is the set of points at which the surface, set of points at which the surface intersects a plane. Intersects a plane that is parallel. That is parallel to one of the coordinate planes. And the reason why we specify specifically coordinate planes is we don't want any random plane at any random angle. We want it to specifically be parallel to either my x, something with the x-axis, something with the y-axis, something with the z-axis. So I don't know how many of you guys grew up with those veggie cutter things, where it's just like you stick your tomato underneath it, you press down, and there's that blade that just right down. Now, if you're only to do that once, what happens is essentially that blade that's coming down is like that plane that's coming down. And what's left is you can see if you were to then take the whatever that incision cut you've made and describe that set of points that you trace. So if let me draw a picture here. So if I have a kind of like a little, and this is rounded. So the dotted lines are to provide like depth perception. This is a three-dimensional object. Now, if I were to take basically, if this is existing in the X, Y, and Z, I'm not allowed to just take the plane that slashes through sideways like that, because that would not be parallel to a coordinate plane. I need it to be parallel to one of these coordinate planes. So what do you guys want to do, X, Y, or Z? Well, you managed to say all three at the same time. Okay, we'll do all three. So X, if we're going to cut it like X, that means it's going to be parallel. And so we're going to be dropping down a slice kind of through here. And so if you cut that, what's going to happen is you're going to kind of cut your thing. And what's going to be underneath is this trace. So you can imagine like here's the right side if you were to cut like that. Yeah, that works. I know that is not artistically beautiful, but is it good enough to see what's going on?
So like a trace of isn't it like a trace of two cones facing each other is could be a hyperbola or a parabola, or like we learned that at the end of Calc 2.
And actually that what you're describing is pretty much the way we characterize all the quadric surfaces, is by what kinds of traces, what shapes you'll get when you take traces. So this is the idea. So this would be like X, right? We take waching, and then now you've got like a parabola trace. So this parabola right here is the trace, because that's the thing that's splitting your function. If we would have done something like this, so for slicing, we take a plane that slices it on top like this. If you look top down, what shape is going to happen?
Circle.
Right, you'll have some sort of a circle shape. So then the trace from a top-down view is going to look like this. And depending on how far up or how far down you are, the circle is going to be smaller up here because you have a little bit small. And then if you slice deeper and deeper, that circle radius is going to get bigger and bigger and bigger. So these are like multiple traces of that shape. So this is kind of giving you altitude. This is the very top trace. This is if you go a little deeper. This is if you go a little deeper. Make sense?
This would be parallel to the z-axis.
This would be parallel to the XY plane.
Okay.
So the XY plane and going flat. And just so it's clear, plane requires two of them. So there are three planes that we're interested in: the XY, the XZ, and the YZ. Those are the three coordinate planes.
The first one we did was xz or xz.
Yeah,
All right, and that would look pretty similar to yz.
right, because it's symmetric.
All right.
Yeah. So we're going to exploit that symmetry. We're going to look at these quadric surfaces. Any questions on this before I move on? Okay. Again, if you want more like satisfying visuals, the textbook can provide that with far better than I can here on a whiteboard. Or in one sense, I'll just ruin cooking for you as a whole, and every single time you go cut the ham at Christmas, you'll think of the trays when you cut it back down, like, dang it!
Wait, hold on, do that?
Ham is very rich flavor, X, Y, and Z. Yeah. I mean, I hope it has X, Y, and Z. It exists in 3 dimensions. You got a ham. If you served a flat ham, I'm not eating that. But yeah. Find ways, especially with these more geometric things, find ways to try to apply them. Because it's those little 3-second reminders of the content that you're learning that's going to instill the information far more than sitting down and grinding it out for 4 hours at a time. Dr. Harder, one of these days before I graduate, they're gonna give us a good whiteboard in here. We can pray. I know, they should really move us to like LR, I think it's 204E or something like that, where they've got 2 massive whiteboards.
Hear me out. Explain the high core lab.
Honestly, I might do that for that one of these days. Okay,
If you go
so
through the libraries, tighten the bolts in the library.
everyone knows about general forms, and there's gonna be no difference with the quadric. So quadric surfaces. What I'm gonna write here is not what you're gonna memorize. I'm just gonna show it to you because you're paying for this class and you deserve to see it at least once. But don't memorize this, okay? This is gonna be ax squared plus by squared plus cz squared plus bxy plus exz plus fyz plus gx plus hy plus iz plus j. All of this is going to be equal to 0. So this is the general. Wow, that is slanted up. This is the general form of quadric surfaces, where all these a through j is going to just be constants. In the same way that kind of, you have a general form of your quadratic equation. It's basically the same thing, except for calculated version.
Okay. That's a lot of divided Z's.
Yes.
Why is J by itself?
Well, because we need a constant term. So notice that this accommodates every single possible combination you could have with 3 variables. You can have square terms of each of the 3 variables, and then your combinations, right? So your points, the xy, the xz, and the yz. And then you need to accommodate just the variables by themselves without being squared. Then you need to accommodate the fact that you could just have a number hanging out in your equation. So this is all of the different, yeah.
Why is there no X, Y, Z?
Very good question. The proof for that, I have no idea.
Oh.
But hey, you could look it up. Reading on your own, that's called initiative. At least some people would call that.
And so what shapes can be accommodated, can be calculated by this equation?
Well, we're about to cover 1, 2, 3, 4, 5, 6 shapes that you'll need to know that use this form. Don't memorize this, but you need to see it. So this is where all the stuff we're really coming from is going to be just variations of this. Okay. A few tips for graphing is going to be, we're going to always go for the intercepts and these traces. So I'll outline all of these. So I want you to pretend like this is calc-free version of your Pokemon Go here. So these are all the character profiles. We're gonna start with the ellipsoid.
Cool.
Don't overcomplicate this. An ellipsoid sounds kind of like what it is. It's an egg. Because you got an ellipse, just now 3 dimensions, so it's an ellipse all the way around.
It's an ellipse-ish.
So this equation is going to look like x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. And the information on the traces is that all traces, regardless of how you try to cut this thing up along your coordinate plane, those traces are just going to be ellipses. And I don't want to spoil what this actually looks like, 1, because I can't draw, and 2, you'll make you read your book, okay? So if you want visualizations of all of these, there's a nice summary page at the very end of the section that simply puts all 6 shapes, all 6 formulas, all 6 traces. So frankly, this is the one section I will accept if you don't even read the actual section, you just skip and read through that summary page, because that's pretty much the entire thing right there.
This one.
Yeah.
Well, that is a question that it's 128. So if I wanted to explain it, then we couldn't get the other 5. But the textbook works through why all of these equations exist. But my job right now is to make sure you just see all of the equations so you can get it written down. Okay? Elliptic paraboloid. Okay. Well, that sounds like what familiar object? And then, well, elliptic, okay, so this is basically going to be now the 3-dimensional version of the parabola. You take a parabola and you spin that thing around and it's going to form kind of like the nose of a plane kind of a shape. This equation is going to be z is x squared over a squared plus y squared over b squared. And look how it's reminiscent of a parabola equation. If you were to cover up one of these variables at each time for a trace, it starts to just look like a regular quadratic, a regular parabola. And so these traces, so the traces with z being some z naught, that's positive at least, this are ellipses. So that's where the elliptic comes apart. And then traces with x being x naught and y being y naught are parabolas.
Is there any one dominant shape? So calc 2 is like parabolas, maybe some of the two. Is there any dominant shape in calc 2 for 3 dimensions that's used?
A typical example that's used a lot is the elliptic paraboloid, just because it's the most accessible example for later when we do polar integration. But in general, I'll point out the ones that are less common, but these are kind of like the main players. Like all of them are to some extent important, because it's like that's a lot of equations. So narrowing it down to just 6 is pretty good for the ones that are going to be important.
What's that last word?
It should say parabolas, but it doesn't look like it. I'll fix it.
That's why x,
Parabolic.
that's x equals x initial, right?
Yeah, x naught.
There we go.
And what if the
Parabolas.
traces with z equals to?
So z being equal to z naught, this is a way to indicate I'm going to fix some sort of trace at a plane height that is positive. So when you look in the textbook and you see the pictures that accompany each of these, lots of these little random specifications will become pretty visually intuitive pretty quickly when you see what's going on. But if I give you too much, you'll think you don't have to do any work on your own outside of class, and then everyone fails. No, we don't want that. So read the book, go to that summary page, look at all the shapes, and check the traces for yourself. Compare these descriptions of the traces and see if you can actually geometrically see what's going on. This is not super hard, it's just a tiny bit time consuming. So spend like half an hour going through the different shapes and you'll be fine. Okay, so hyperboloid. There's going to be 2 kinds of hyperboloids now that we're in 3 dimensions. So this is of 1 sheet. And visually, that means it's just going to be one continuous kind of 3-dimensional function here. Whereas the one with 2 sheets is going to be shockingly 2 separate sheets. This equation form is going to be x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. And your trace information, so the traces with z being equal to z naught, they are ellipses. And that's actually going to be true for all Z naught. So I don't know if you guys have seen this symbol before. I'll write it up here in bigger font. An upside down capital A. Chelsea, do you remember this from a linear algebra? I think I used it. What does it mean? Did everyone hear her?
For all.
Good. This means for all. And then sometimes, sometimes we say for each or for every, but the idea is basically every single possible case. So now here, this is not true for all because Z naught has to be positive. That's a restriction. Here, there is no restriction. So long as basically the only restriction is that we don't randomly choose like, a complex or imaginary number, it's going to be good for all real numbers or all real constants Z naught. Okay. And then the traces with X being X naught or Y is equal to Y naught. Again, these are general, it doesn't really matter what those are. You're going to have hyperbolas. So these are hyperbolas. I don't know how well your high school prepared you on conics. I was just irresponsible in high school and I skipped over conics, and so I had to relearn all of these 2 years ago. But
What does that say after ellipsis?
here,
No, after that. Yeah.
That is.
so that's the symbol
For all.
Oh, okay.
for all Z naught.
Oh, okay.
Yep.
The formula for hyperboloid and ellipsoid is the same. So how do we distinguish between the two?
Plus one's minus. Yeah. You add.
Oh, I got you.
Yeah. So, but you do bring up an excellent point. It's not like these are crazy different from each other. So if you remember this one, and then remember, oh, Sam Patchen in class on Monday pointed out that they're really close, and the only difference was a minus sign. Well, boom, now you've memorized 2 for the price of 1. Okay, so take advantage of smart memory. I'd be the first person to agree with that strategy because I hate memorizing things. Okay, everyone good with these 3? So this is the first half of the shapes. Okay, no worries. And while people are writing this down, as a disclaimer, in the Pearson, so the kinds of questions they'll be like, it'll give you a thing, and they'll say, identify, blah, 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 okay? It's not always going to be given to you in just exactly perfect, beautiful textbook form. So sometimes you might have to add something to both sides, or subtract some things from both sides, or rearrange it, or get a 1 on one side. You know what I'm saying? So to some extent, these are just these are the general formulas, but this does not preclude using your own personal creativity to find these forms. So that's why you have to be aware of what forms to be looking out for. Because the Pearson is not going to just, it's going to indiscriminately just choose something. You don't really get to know what that is. Now, sometimes they might tell you, they might specifically say, hey, I'm looking for the form of a hyperboloid in one sheet. But sometimes they might not. And so depending on what information you're given, be able to interact with the algebra to get and recognize these different forms. Okay, we good with writing everything down? Thumbs up. Oh, yeah.
Is it possible for the Z value to be negative for ellipsoids and hyperboloids? Because if it's only one negative sign for the Z separating them, it's possible for the Z value to be negative and confuse you.
That's a good question. I'll answer that with this question. When you're told that a function is defined to be y is equal to x squared, if you're concerned whether or not the y is going to be presented to you as negative, or do you understand that this is dependent on what the actual 2 variables are going to be? So that's kind of like here. So it's really possible for Z to be negative.
It is, but they
What combinations of x and y's are you throwing into the soup to spit out a minus number here? Because these are squared. So that's why this specification has to be made. Because this surface simply doesn't even exist below the xy plane. So that's why but whereas the hyperboloid, that indiscriminately is going to be able to go. So that's why it's all clumped implicitly on one side. So the explicit kind of forms that are going to be reminiscent to old function definitions are going to be understood more like that. Whereas if everything's put together, all the variables are smashed on one side of the equation, think about that more in terms of, that's more analogous to when you learned the basic equation of like unit circle. So this isn't, now you're not really concerned about like, oh, which was gonna be positive or negative, we understand this to not really behave the same way as an explicitly defined function. So then we put all the variables on one side. Okay, but those are good questions. Anything else?
Is it fair to assume that if we see z not raised to the power of 2, that is the paraboloid?
Bingo to the idea of if the z is not being squared, then it's going to be one of the explicit forms. But the hyperbolic paraboloid is an explicit form of z, but it looks different. But yeah, you are right. So that is a characterization thing. So if you're given an equation where the z is not squared, well, you just wiped out, I think, 4 of the 6. And so it can only be between 2, yeah. So use clues like that. Learn how to observe. Find patterns for yourself. That's going to be the best way you can handle these kinds of shapes. Because realistically, at the end of the day, this information is used in application far more than just for the sake of doing it. So get familiar at that level. Can I just find that equation and then apply it to some other intermediate step in a problem? Okay, I'm gonna erase these and then here write out the rest. I set this down. So now, following the hyperboloid of 1 sheet, what do you think is coming next?
2 sheets.
Yeah, hyperboloid of 2 sheets. So the equation form for this is you're gonna have negative x squared over a squared, and you're gonna have negative y squared over b squared. Whereas you have a positive z squared over c squared and minus. So in this case, now that is distinctive because again, the x squared and the y squared, that's always non-negative. And so now by putting the minus sign out front, you guarantee that those are going to be negative. And so these traces, with z equal to z naught, and there's going to be a specific condition for that magnitude of z naught. So because it's 2 sheets, that means there's going to be a gap between them. So this condition is going to make sure we're not slicing thin air. We want to actually be slicing the surface. So where the magnitude of z naught needs to exceed the magnitude of c, because this magnitude is going to indicate kind of when, yeah.
That's equals 1, right?
Yes. And I'll rewrite it. My pen is kind of blinking a little bit.
Uh-oh.
There we go.
Have I touched the hem of Jesus as well?
Does this one go above the XY plane?
Yeah, so this is going to be one that's going to be like, you're going to have a piece up here and a piece down here. And so this condition is going to make sure you're not just slicing into thin air in between those two things. So that C is going to be indicating when the surface actually resumes again.
Is there one shape that's restricted to below the XY plane? Strictly heavy.
You could define a paraboloid as such. So in the same way that you could define a paraboloid y equals minus x squared, well, now this is 0 and everything below. Yeah, so stuff like that can happen. But you can get comfortable with manipulating the shapes once you understand the base definitions. And again, go through the text, find that summary page, and it'll all click when you see the visuals. So here, the bit with the traces with z and z naught, these are ellipses. And the traces with x being x naught and y naught are hyperbolas. Okay. Now there's the elliptic cone. Someone actually brought this up right here. That's good. we have x squared over a squared plus y squared over b squared is equal to z squared over z squared. This is different in that sense. And now we've pushed the z squared over on the other side, even though it's still technically squared. And the traces for a cone, as the elliptic cone, traces with z equals z naught, so long as they're non-zero. And the reason for that, you'll see visually, but I'll give a rough sketch. Basically, what's happening at 0, that was terrible, is there's this point of intersection where it comes down to a single point. That's like what's happening is you got this cone up here, you got a cone up here, and right at that, there's nothing. So we're not including the trace where there's nothing. These traces are ellipses. So lots of traces are ellipses in general. So when you look at the pictures, it'll make sense what kind of shapes we're dealing with here. Traces with x is equal to x naught or y equal to y naught are hyperbolas. Or intersecting lines. Now, the intersecting lines case is very specific to a certain property, but I don't want to spoil that one for you because that's kind of fun. So when you look at the pictures, you can verify that one.
Is that elliptic core cone?
Sorry, cone. Yeah, it's an N. If I'm not careful, it'll put me in penmanship. Okay. And then the last one is the hyperbolic paraboloid. I'm trying, and the more I try, the worse it gets, so I'll stop trying and see if it's readable. Okay. So this, I think, yeah, Rebecca, this is the other one that has the explicit definition, because now we just have, again, a singular z on one side, and it'll be x squared over a squared minus y squared over b squared. So our traces with z equal to z naught. We also don't want this to be at 0 because there will be nothing there. These are hyperbolas. And traces with x equal to x naught or y is equal to y naught are parabolas. I like this shape, is kind of really cool. It looks like a horse saddle. So I'll call that. This is not a math term, but it's a memory term. When you look at the picture, that'll make more sense. So actually, can everyone go to the textbook on their computer right now? And then since it's, let's see, it's 1.7. Okay, so what's going to happen is you're going to go to the textbook. Go to the summary page with all 6 of these quadric surfaces that we're going to be talking about for the rest of the class, really. And then once you can basically like bookmark the page or something, save the page, and then you can be dismissed. Just make sure you have that page read, make some flashcards on that, and then have that ready to go for tomorrow and going into the future stuff. Because when we move out of chapter 13, chapter 13 still is going to follow you around for the rest of the class. It's all the language of vectors that we're going to be using. So, and also because I don't like giving people exam and like review related stuff until the weekend before. Chapter 13 is kind of big, so half of it is chapter 13. The important stuff like projections, the different kinds of products you can do with vectors, work, the definitions of the different products like dot product and cross product, lines, obviously planes, those kinds of things. Those are the important takeaways that we're going to be using for the rest of the class. So go through the process of making sure you're familiar with that. Chapter 14 isn't gonna be too bad, and then there'll be a test in like 2 weeks. Okay,
So this is 13.6.
yes, this is 13.6. So find the section in the textbook that summarizes all these with the pictures, and then you're good to go.